Okay. Good afternoon, ladies and gentlemen. My name is Andini Dingan Ayumurti, and I hope you're all doing great in this beautiful day because I'm glad to share my presentation about performance optimization, battery balancing, using multi-stage method based on multi-winding transformer and single inductor. So, my presentation content would be includes of introduction, methods, results, and end with conclusion. So to start with, I want to elaborate some introduction and the key point on why the unbalanced battery cells occur and it's important on the battery management system to have cell balancing system. So the first one is we might have been noticed that the increasing trends on electric vehicles is being desired in throughout the years. And to provide the sufficient desired energy for electric vehicles, it is important to support a large number of lithium batteries that are being grouped in series and also in parallel. But unfortunately, this battery that is being series and also parallel connected are not always have consistent characteristics like self-discharge rates, ambient temperature, coulombic efficiency, and etc., which may lead to the imbalanced state. So the next one is I wanted to focus on series connected battery and the illustration that is depicted as A, which is the initial unbalanced state of charge distribution. And when it comes to the discharging state, we know that it is impossible to discharge one cell without being over-discharging the other cell. And it is also valid when it comes to charging a cell without being overcharging the other cells. And of course, we don't want this to be happen since over-discharging and also overcharging would affect its efficiency and also the unused discharge capacity and also unused charging capacity would affect its efficiency too in the overall energy systems. So we might have to notice that the balancing system is very important in battery management system. But the question that might have to occur is how we provoke and perfect to create the perfect balancing characteristic for our system. So, of course, by any chance, is everything or any characteristic that is so-called as a perfect system, which is including high efficiency, simple, fast balancing speed, heat, and also doesn't take up a lot of space. And of course, I wanted to focus on how cell balancing topology is divided into three main parts, which is the passive balancing topology or resistive balancing, that is consists of, by its name, resistive component that is dissipate energy. The second one is our main concern here is active balancing topology, which is consists of the active components that can store energy like capacitor, inductor, transformer, and also power converter. And the next one is hybrid balancing topology. So the main focus on this research to have been used the multi-winding transformer as our base of active balancing topology. And this method has a wide range of advantages in comparison with the other balancing topologies, like the fast balancing speed and also simplicity of its control system that is make this balancing topology is highly desirable. But of course, every system has its own drawbacks, like in this topology, there is a limited number of windings that can lead to the limited number of cells with the balance. So, as I previously mentioned, the limitation of multi-winding transformer led to the previous research on how to modularize multi-winding transformer. So the first research is done by Lim in 2014, and the modularization technique is being introduced with the concept of magnetization energy that the current would be automatically occurs from module 1 to module 2. But the drawbacks is there is no complementary components, so the current would be uncontrollable. And the second research is done by Dewey in 2018, which is when we see these two topologies, there's a distinct difference that is, there is the complementary elements like switch capacitor as a balancing component between modules. But based on our study and also research, we found out that the switch capacitor has relatively low balancing speed in comparison with the inductor. So we might have to notice and simply we propose the topology to substitute switch capacitor with a single inductor and we are expected to optimize its balancing speed and also to minimize the number of switches that have been used. So here is our experimental setup and our hardware setting with each of components and also parameter is being described in the table that are shown. So we have three main parts in our experimental setup that is consisting of our switching module, our balancing circuit, and also our cells, and our sensor module, which is consists of voltage sensor and also current sensor. And every component that have been mentioned is described as the parameters that is shown in table below. And the next one, we set our parameters and also assumptions, which is our analysis parameters would be the first one is balancing efficiency and its voltage drop or losses. And the second one is our balancing speed, which is our main concern, and it is very linked with average balancing current. And some assumptions are being made, like the first one, external factors are being ignored, and we use the fixed switching parameters, and the third one is internal condition for each battery cells are considered as equal. So the following table shows the initial voltage for our cells battery, that is we use for cells battery with two moduli, that each module will consist of two battery cells. And our switching parameters is set with fixed frequency and also fixed duty cycle for multi-winding trafo and also for inductor, which is our multi-winding trafo will consist of the frequency about 65 kilohertz and 65% of the cycle, and our inductor will be 35 kilohertz and 55% of the cycle. So we jump out in our result, which is our proposed topology that is being shown in the line chart and also our bar graph. And we see that our proposed topology in cell 1, cell 2, cell 3, and cell 4 has initial voltage condition about 0.287, which is difference between cell 1 and also cell 4, and which its final voltage condition about 0.049 volt in about 700 seconds. And besides that, we analyze its voltage drop and also its efficiency based on the initial cell voltage and also final cell voltage for each cell and also modular level. And we see that we have efficiency around 81.8% for modular level and also 89.89% for cell level. And we have its losses about 0.54 to 0.58%. And we might have been seen that our proposed topology, that is inductor, have relatively fast balancing speed for about 700 seconds. That is really analogous to its average current for about 200 milliampere. So to compare and contrast with our proposed topology, we did some research in the switch capacitor as our comparing. And we see that the voltage balancing result for the multi-winding trafo and also switch capacitor base is shown as the graph. And we see that with the initial voltage cell condition that is slightly similar with the previous result, and it is take about 3000 seconds to reach its final voltage condition about 0.095 volts. And of course, we did the same analysis for its voltage drop and also efficiency with the previous research, and we have the results of around 94 to 95% of the efficiency and also its voltage drop around 0.14%. Now, we might have been seeing that we have a slightly higher efficiency in comparison with our proposed topology that is inductor based. And of course, we might have been noticed that the switch capacitor base has a relatively slow balancing speed, which is around 3000 seconds. That is really analogous, which is average current for about just 10.62 milliampere. So those are our results, and we might have been jumped to our conclusions for today. So the first one is, of course, our proposed topology is proven to optimize the modular balancing speed in comparison with the previous research, which is the switch capacitor base. So our proposed topology is reached its voltage gap that is around 0.049 volt in about 700 seconds. and the switch capacitor base is around 0.095 final volt for about 3000 seconds. But however, our proposed topology is shown to have an efficiency that is slightly below in comparison with switch capacitor, which is around 81.8% in modular efficiency, whilst the capacitor base is about 94.6% in modular efficiency. So we suggest the further analysis and also the further improvement for the next research in our system, that is the further consideration and calculation for inductor, and also the development for control algorithm is needed and necessary to boost its efficiency of our system. So that is my presentation for today, and good afternoon for you all.